Okay, I would like to welcome you all to our next lecture of our POLAB lecture series. And today I have the pleasure to introduce Professor Matthias Ihme, who is a multiple award-winning associated professor in the Department of Mechanical Engineering at the University of Stanford. After receiving his PhD in mechanical engineering from Stanford, he spent 5 years at the Department of Aerospace Engineering at the University of Michigan and returned then to Stanford. His research interest areas are modeling of reacting flows, development of numerical methods, and also the investigation of advanced combustion concepts. And today he's going to talk about heterogeneous combustion in porous media as ultra-low emission combustion concept. Welcome, Professor Matthias Ihme, and I give the word to you.
Thank you very much. Let me share my screen. So it's a pleasure to have the opportunity to present this, and I think with all of the remote sensing or remote meetings, this makes this rather convenient. Also, I enjoyed traveling to Europe now these days. So thank you for the invitation. What I'd like to do is the next, I think 45 minutes or 30 minutes to give you an overview about the research that we have been doing over the recent years on exploring porous media combustion technologies for the applications to gas turbine engines, but general combustion concepts with a goal to reduce emissions. And I want to start out with showing you some practical applications of porous media systems. And I know that at your center there is quite some work in this, and I expect that there is certainly some overlap of interests or commonalities. The topic that I want to address in this presentation is applications to combustion. What you're seeing here is a classic example of a porous media burner. I will talk about this later on, where we are trying to burn inside this porous structure with the goal of recuperating the heat or extracting heat from the combustion products and utilizing this in a rather efficient way. Other applications are heat exchangers, as you're seeing here, where we're using the ceramic forms as a very active and an internal heat recuperation systems. I think many of you are familiar with thermal protection systems on atmospheric re-entry systems in the form of ablators, where we have carbon fiber structures in a rather porous, dense medium here with the goal to ablate this, to burn them off, and with this liberate heat. Other applications are mixing systems, flow systems shown here in the system, filtration systems, for instance, in catalytic converters, but also porous medias in a rocket propulsion system, just as a way for homogenizing the mixing system, and with this getting a very stable fuel supply. So what you're seeing here is this field is rather broad in its applications. As I said, what I'd like to do here is to focus on one particular applications, and this has to do with this porous media combustion. And I hope by the end of this lecture that I can give you some physical explanation on why we would like to explore this porous media systems, address some of the research challenges, and show you some advances on how we can step one or make some advances towards enabling this technology. So to motivate this this work, I have here in slide, this shows you essentially the emission reductions in aviation, gas turbines for aircraft applications. And what you should take away from this is nitric oxide, which is a very strong pollutant responsible for greenhouse gas emissions, for ozone layer depletion. And what you're seeing is over the years, there are some rather aggressive goals of reducing the NOx emissions, in this case, nitric oxide emissions. And the latest stage was a reduction by about 12%. And that's significant, which really tells us that conventional combustion technologies that you might be familiar in gas turbine combustion systems are just not able to scale to meet those challenging requirements. And at this point, this was about 4 years ago, NASA initiated a research activity with the goal to identify novel combustion technologies that allow us to increase the emission regulations, or to meet those increasingly stringent emission regulations, facilitate higher energy densities. What this means is that we want to liberate more heat for a given volume. And I show you here some ideas on how we can achieve this. And at the same time, we also want to push to renewable and fuel flexible applications. This means the utilization of biorenewable fuels, of alternative fuels. And you can really think about this, that technologies that are currently used are challenging to scale or apply to different fuel systems. Okay. So what we decided to do at this point is we essentially explored this concept of porous media combustion. What I want to do here is to give you first a physical understanding of this problem, since I assume that not many of you are familiar with combustion in this heterogeneous environments. And then move forward to give you some tests, demonstrate the feasibility, and slowly work our way towards some of the more advanced combustion challenges here that we seek to address. So what you're looking at here is a so-called porous media combustor. This porous ceramic structure, as you're seeing here, this is this metal foam, or in this case in ceramic form, could consist of different materials such as alumina, silicon carbide, but also some zirconia stabilized materials. The pore size, as you see here, is somewhere between a few millimeters up to a half centimeter, 5 millimeters in diameter. And what you can think about is you're seeing already two different pore structures, some very small pores and some very large pores. The idea here is that we are splitting this burner in two different sections. The first section is in so-called flame arrestor. The second one is the combustion zone. So what we like to do is we like to liberate the heat in this upper combustion zone. And this flame arrestor is here essentially installed so that we are preventing the flame from moving backwards towards the unburned fuel mixture. So this is mostly in safety feature. And you can think about this: if your pores are very small, you're essentially not able to propagate in flame through this very small pore sizes, and you would essentially quench the flame. So what I mean with quenching here is simply a way that the heat losses of the flame exceed the heat liberation, and by this we're extinguishing the flame. Okay. So what I'm also plotting here on the left-hand side is the temperature profile. What you're seeing is it is essentially smeared out, it's broadened. And the reason for this is that the ceramic foam is a very good heat conductor. And with this, we're exchanging the heat between the flame and the ceramic foam. And you're seeing eventually, or essentially, that heat is conducted upstream into this preheat zone, where we're essentially using this heat in a very effective way to preheat the incoming reactants. And this is just one way to extend the combustion flammability limit. Okay, so in principle, we are mixing, or we are injecting a fuel-air mixture from the bottom to the top. We are stabilizing the flame somewhere right around this flame arrestor in this transition zone. We are extracting the heat, the combustion heat, from the gas phase by the ceramic foam, conducting this upstream, and then we have essentially a very efficient internal heat recirculation system. And this is really the way for achieving this interesting combustion properties. Okay. Why is this technology particularly attractive for a number of combustion applications? And what I'm thinking here is gas turbine applications, boiler system, stationary power supplies, but also stationary gas turbine systems. Number one, we can achieve an extended power modulation. This really means the range over which we can operate in combustion system. If you have conventional combustion systems, this is typically a very narrow range here because of this very strong thermal mass that we have in this porous media, as we can operate this over in rather extended operating conditions. I'm going to show you in a second that this system is particularly attractive to reduce carbon monoxide and nitric oxides. These are pollutants which are heavily regulated, as I showed you from this previous slide. And by utilizing porous media combustion, we can reduce those pollutants quite significantly for these applications. We can burn at ultra lean conditions. What I mean here is, if I recall, combustion applications under ideal conditions, we're burning at stoichiometric mixtures. This means we have the right amount of fuel and oxidizer so that we can convert all of these reactants into products. This is called a stoichiometric mixture. If you have excess oxidizer, you're calling this a fuel lean system or fuel lean mixture, and there will be an flammability limit where we just have not enough fuel in order to burn all of the oxygen, and this is called a flammability limit. So now with this porous media combustor and the trick of recuperating the heat, preheating the reactants, we can essentially extend this lean flammability limit by as much as 20 to 30%. And this makes it rather attractive, simply for the reason that we can now operate at much leaner or fuel leaner conditions than we can do at conventional conditions. And this makes it a rather attractive system. Another attractive for gas turbine applications is that we don't encounter thermoacoustic instabilities. And thermoacoustic instability is a coupling process between the pressure waves and the heat release in a resonant fashion. And this can essentially result to instabilities to the damage of the combustion system. Here for this porous media burners, we have the advantage of suppressing those thermoacoustic instabilities simply for the reason that this porous media burner acts as a disperser, so where we're dispersing the acoustic waves, and this coupling is essentially extended or suppressed. Noise emissions and in fuel flexible operation are two other applications that makes the system particularly attractive. And what I like to do here in this presentation is to confirm this through experiments, and at the same time also illustrate a modeling analysis approach where we are pushing those limits even further so that we can extend this operability regime. Okay. So then let me briefly talk about the operating principle. I mentioned this already before. So I have the same combustion system. I'm injecting now, or I rotated this burner by 90 degrees. The fuel or the reactants are coming from the left-hand side. In this case, I'm mostly looking to gaseous fuels. We also have investigated pre-vaporized liquid fuels. We are sending the reactants through this combustor because of this internal heat recirculations. We are preheating the internal those reactants between the stage 3A and 3AX. This is the preheating zone. The combustion zone is this very thin layer where we have this instantaneous combustion process, and you're seeing this by this flame region. And the second region, this rather extended cooling region, is essentially in bay here for extracting the heat from the combustion products. And with this, we exhausting this system. Okay. Now, what we have done is, in the first case, is to convince you that this is actually a viable tool for gas turbine applications. Again, motivated by this NASA applications, we did a basic design analysis. This is a thermodynamic analysis to investigate the feasibility of this porous media burner. I think many of you probably recall a schematic of a gas turbine combustor or a Brayton cycle engine. We have a compressor system, we have a turbine, we're extracting work from the turbine, directing this in order to compress the gas. And this system here is a schematic of this porous media combustor. You're seeing the preheat zone, pH, the heat recirculation zone, RC, and the combustion zone. And we're using the same principle here. So what we did is we performed a thermodynamic analysis, which is introduced here in this paper by Daniel Mohades, a graduate student in our group. He did an analysis to demonstrate the viability, and I want to show you the key results here from this analysis. So this is essentially a thermodynamic cycle representation where we're looking to a Brayton cycle. This is a ratio of the temperature as function of entropy. In classical analysis, what's certainly more interesting is to plot this in a pressure volume diagram. And what you can recognize here is that by utilizing different combustion operating conditions, fuel lean conditions, as indicated by this value here, this phi over phi naught, my notation of phi means this equivalence ratio. If this is 1, we are essentially matching the notional operating conditions. If this is less than unity, we are operating this under this ultra lean or leaner operating conditions. And by this, you've seen that we can operate the combustor at much higher pressure ratios. And this is really here in way to increase the thermal efficiency. Without going into too much details, I want to show you the key result here in terms of improved thermal efficiency and improved emissions. So what I'm plotting here is now the operating conditions or the performance of this gas turbine combustor as function of this normalized equivalence ratio. As I said, if this is unity, we are considering in conventional gas turbine cycle. In this case, this is in Siemens engine. Our porous media burner allows us to push this to very lean conditions, as lean as 0.7 normalized conditions. And with this, you're seeing that we're increasing the pressure and at the same time also the thermal efficiency. So this blue line here is an increase in thermal efficiency. And what you're seeing is, if you look closely, we are able now, by installing this porous media combustor, that we are increasing the thermal efficiency by about 20%. And that's a significant improvement in over conventional thermodynamic cycles. And this makes this particularly interesting for a number of applications. At the same time, if you look to the figure on the right-hand side, I have NOx emissions and the carbon monoxide emissions. And what you're seeing here is that, again, if you're operating at very lean conditions, we have the added benefit that we can also reduce the emissions by a factor of 2. And again, that's significant and noteworthy for practical applications. Right. So with this, I think I gave you motivation for exploring this technology further. We are seeing benefits in improving the thermal efficiency. This really means fuel consumption. At the same time, we're seeing significant improvements in the emission reductions, both for carbon monoxide and for nitric oxides. And with this, I want to touch on the more fundamental challenges. And you might ask, well, this looks all great. Why is this not utilized in practical applications? And I think this slide here summarizes the key challenges, mostly illustrated here on this figure. These porous media combustors are rather complex systems, simply for the reason that they are integrated systems. We have to deal with the coupling between the flow physics, the strong heat transfer, the material properties, and the combustion chemistry. And all of this makes it such an interesting environment that we thought it's worthwhile to develop a research program around this effort. Right. So what I want to do here is, in the remainder of this presentation, walk you through 3 different challenges that have to do with the characterization, with the novel design, and the additive manufacturing of the different or tailored porous ceramic structures, with the goal of increasing the efficiency and utilizing these porous media burners for combustion applications. So let me talk first about the characterization. Remember, in the first result, I showed you a theoretical analysis where we recognized improvements in the thermal efficiency and reductions in the emissions. And the practical application, or the question here, is on whether we can confirm this through practical applications. In order to do this, I want to show you here already some variability in the combustion system. And this is illustrated on this table here. What I'm plotting is 3 different material properties of the ceramic porous form. In the previous slide, I showed you mostly silicon carbide porous forms, but there are different materials that we can utilize. And this is, for instance, alumina, silicon carbide, and metal alloys in the form of zirconia oxides. And as I said, a key aspect of this porous media burners is this very strong coupling between the combustion process, the heat release, and the heat recirculation. And there are different requirements on the material properties. We need to sustain in very high temperature. The thermal expansion is a challenge, and this is really the material expansion due to the cyclic operation. What you can imagine is we have very strong temperature gradients. So we want to make sure that the thermal expansion of these materials remains very small. Otherwise, we're losing the integrity of the structure. Thermal conductivity should be favorable so that we can extract as much heat and redirect this. Thermo-structural emission resistance is another issue, which is here essentially a proxy for the operability on how fast can we heat up the system, how fast can we cool down our porous media burner. Emissivity is mostly a process in order to describe the radiation. And with this, we have different ways for tuning and modulating our porous media burner. So that, to give you an idea here for the different systems, these are a couple of samples that we typically use, an yttrium stabilized zirconia. The diameter is about 5 centimeters here in the cross section, and the pore sizes, as I said, is somewhere 5 millimeters. The key parameter here is the units of PPI. I'm sure that you are very familiar with this. These are 10 pores per inch. We are here in America. We like to use units of inches. So this really translates to a pore size of around 2.5 millimeters. And the same is true for the silicon carbide, right? So what I want to show you here is that depending on the selection of the material, we can tune different parameters, different material properties. This is illustrated by this first parameter, the thermal conductivity, and the same, or the second parameter that we can modify is the pore density, this pores per inch in the units. And I'm just showing you here different permutations on the setup. A typical burner that we are utilizing is about 3 inches in length. So this is about 7.5 centimeter. The diameter is roughly 5 centimeters, so 2 inches. And by looking to different ceramic structures, we can adjust the different performance metrics. And this makes it so rich for practical applications that we have different ways of designing this porous burner. To illustrate this here, what you can think about is if you have a very low thermal conductivity, as for instance illustrated in this zirconia material, you can imagine that this is a rather poor porous media burner in the sense that we can mitigate or that we can constrain our operability. If you have very favorable heat conductions, for instance, utilizing the silicon carbide, we can extend the operability of this burner. Okay, to illustrate this, we have done different experiments, different materials in the upstream flame arrestor, where we're using silicon carbide and this YZA, yttrium stabilized zirconia. And in the combustion region, we're primarily using silicon carbide. Right? So what I'm showing you here is a conventional burner setup. It's a rather simple setup where we are injecting a premixed fuel air mixture. You're recognizing maybe here the 3 burners, the 3 porous media burners. They're insulated. And if you look in the system, the flame would essentially look like this red glowing system. What I want to emphasize here is that's not the flame that's glowing. It's really the ceramic structure. So we're really pushing this to the limit of the operability. And it's essentially the radiation, the light radiation of this burner that you're seeing here. In terms of describing the performance of this porous media burners, we're using essentially primarily a visual inspection of determining the flame stabilization. What you're seeing here in the first system is, if you're looking from the top, you're seeing this very homogeneous flame temperature, this heating system. That means that the flame is well anchored. This middle region here, you're seeing that the flame slowly starts to break through. We're seeing some dimming here, eventually the loss of the flame, and this final stage means that the flame detaches, it's pushed to the top of the flame of the burner. And with this, we are not stabilizing the flame anymore, and it's lifted off. So this is essentially instability limit. And what we'd like to do is to determine the operability or the flammability limit as function of different operating conditions. For our case, this is notionally the mass flow rate, how much fuel and oxidizer we can send through this burner, and the equivalence ratio. Remember, the equivalence ratio is this ratio of the fuel, the amount of fuel and the amount of oxidizer that we can burn. And we would like to push this to very lean operating conditions. Right. So for the first diagram that I want to show you here is a burner where we're using silicon carbide in both regions, in the flashback arrestor and in the combustion region. And you're seeing typical stability limits are illustrated by these lines here. These are measurements plotting the stability limit where we are retaining a flame as function of equivalence ratio and the mass flow rate. through the burner. And the system is in rather small region, simply for the reason that this is a silicon carbide system. And now, if we are switching the material properties to an YZA in the preheat zone, remember the zirconia has a very low heat conductivity. So this essentially prevents the flame from pushing backwards. There you're seeing right away that we get a much extended flammability or stability region. And this makes this rather interesting for a number of combustion applications, right? Figure on the left, where we have very low mass flow rates, this is referred to as a flashback. That means the flame propagates upstream. Figure the boundary on the right-hand side is in blowout limit. That means the flame pushes to the right-hand side and leaves the burner, right? Now, the second regime that I want to show you is if you're changing the pore diameter. This is, again, zirconia. We have essentially a very narrow operability, and the flame pretty much behaves as an pre-mixed freely propagating flame. By changing the material properties again, we're seeing that we can here again modulate the stability limit, which makes this rather interesting for practical applications. Okay. For our applications, for combustion applications, pressure drop is an important factor. We measure the pressure drop for this experiments, and what you can see here is that the pressure drop doesn't exceed 0.4% with respect to the inlet pressure. So this is a rather small pressure drop, and as a matter of fact, it matches the Darcy-4 relation quite well, giving us confidence here that this is a very reasonable estimate to assess the pressure drop. Just give you a reference point for typical gas turbine combustion applications. We're talking about pressure drops of about 3%. So this porous media burner is well below this stability limit. And for different operating conditions, you're seeing that we are falling underneath this four-comma relations, meaning overall there's very acceptable pressure drops, meaning that this is not a performance limitation for this practical applications. Okay. Now, since this was a NASA-sponsored project, one goal was to demonstrate this also at high pressure conditions. What we did here is we utilized a high pressure test stand at NASA Glenn Research Center. This is in Cleveland, Ohio, where they have a high pressure facility that you can see here that is operable up to a pressure of 20 bars. We installed this Porous Media burner, did some tests here, and I just want to share some of the results here as I think they are interesting to also demonstrate the operation conditions for high pressures. Another challenge that we are considering here is the applications of liquid fuels. So here, in addition to using methane as a primary fuel, we also considered heptane, in this case pre-vaporized heptane, in this high pressure facility. And schematic of this facility is shown here. You might recognize the porous media system here. Upstream of the system, this is our pre-vaporizer, essentially consisting of a liquid fuel supply, which essentially emits the liquid fuel. I want to show you some of the key results here from this porous media burner. Again, same diagram. This is done at different operating conditions. I'm plotting the equivalence ratio as function of the mass flow rate. What you're observing here is significantly higher mass flow rates. We can push about 3 kilograms per square meter per second through the system. And with increasing pressure up to 20 bars, we can also operate this at much cleaner conditions. So this makes it very interesting for practical applications. We can push this to rather low operating conditions. If you were to look to temperature profiles through the burner, I'm plotting here the axial locations through the burner. At the top is the exit of the burner, and then we're moving down. You're seeing that we have a rather broad flame zone. The temperature is fairly homogeneous at these conditions. And if you're looking to different temperature regimes, you're seeing that at some point the flame detaches, it pushes a little bit further downstream, but overall there's a very good representation of the flame profile, and we have a rather nice and stable temperature field inside this burner. Right. So this is again an illustration of the flexibility and versatility of this porous media burner. We can operate this at high pressures. we are able to demonstrate this rather low emissions and this extended flammability limit, which I think is a really attractive problem. And now what I want to do is switch gears here, and I want to address two aspects. The first one is the material stability, and this is really the key limitation of this porous media burners. And the second one is the selection of the design criterion. So what we have taken here is some pre-manufactured porous ceramic structures, and if you are observing them during the combustion process, we are essentially seeing that we are forming cracks. So these are micro-CT images at a spatial resolution of about 1 micrometer. Pre-combustion systems look very homogeneous, very well structured. If you're operating this for about 22 hours, which is a typical operating cycle, we're essentially seeing the formation of cracks inside this porous media burner and also some surface oxidation. And this is a limitation of this porous media burners, since we're using off-the-shelf designs and we have currently very limited control over the material properties. And we seek out to address this challenge by introducing additive manufacturing so they can tailor and tune the design for this applications. Right. And so what I want to do is, in the remainder of this presentation, I want to give you some ideas on how we now use computational modeling techniques in order to analyze, to design and tune, or in this case, optimize the porous ceramic structures. And the next step, to employ additive manufacturing processes so that we can essentially manufacture tailor-made porous ceramic structures that are optimal for combustion applications. Okay, so let me jump to this problem, and with this I'm moving to the second topic here. This is a novel design of this porous ceramic structure. Remember, what we took is off-the-shelf porous media structures, and here we want to see whether we can revise this to essentially tailor this. And for this, we are resorting to numerical simulations. We're using a so-called two-zone approach, which essentially takes advantage of the scale separation between the pore size and the flow path. With this, we can write down a set of governing equations. I don't want to scare you here, but I assume that many of you are familiar with this formulation. This is a one-dimensional model, so we are essentially describing the conservation of mass, chemical species, and the energy through this porous media in a one-dimensional setting. X is the coordinate along the porous media burner. And just to explain this equation a little bit more, the first equation describes the conservation of mass. The second one is a combustion equation where we are describing the chemical species. Y is the species vector. And the epsilons here that you see is the porosity, comparing the pore ratio over the retaining volume. You're recognizing here a chemical source term. We have an energy equation here where we have a contribution of the heat release by combustion. And we have a heat exchange term by convection. This exchanges heat from the gas phase, denoted by subscript G, to the solid phase, denoted by subscript S. So we are exchanging heat between the gas phase and the solid phase. This is happening in the combustion zone, but at the same time, we are also exchanging heat from the solid phase to the gas phase in the preheat zone, right? And with this, we're coupling the solid to the gas phase just by the energy equation. And if you look closely, you also have a radiation term. This was essentially responsible for the heat losses by this glowing process, which can be quite significant for certain ceramic structures. Okay. Now, we can do some non-dimensionalizations, and this is really the motivation for this design that we are utilizing. If you normalize all of the governing equations, you're essentially identifying a ratio comparing the Nusselt number to the Peclet number. And I'm sure that many of you can remember that this is nothing else than the Stanton number, the ratio of the interface to convective heat transfer. This is the heat exchange between the solid and the gas phase to the convection. And what we like to do is we like to operate and tailor the system, as this is the key parameter to control the heat exchange between the solid. Remember, very early on in this presentation, I showed you different material properties, YCA, yttrium stabilized zirconia, silicon carbide, and alumina. The combustion performance can essentially be explained simply by this ratio of the Nusselt number to the Packard number, right? So for conventional combustion systems or burners that I showed you in the previous result, we can show that the Stanton number is a function of the mass flow rate through the burner and the pore diameter. And by changing this, we can identify different regimes. For the burners that I showed you in the previous result, the step design, we are essentially seeing that we have two distinct pore diameters. And with this, we are utilizing a rather limited, or we are accessing a rather limited operation regime. And our idea here was to broaden this by utilizing a continuously graded porous media burner. So the idea is, instead of using two discrete porous media or porous zones, we are thinking about continuously changing the pore diameter and the porosity, and with this are able to access this entire combustion zone, right? So this was essentially motivation driven by our theoretical analysis. And what I want to show you in the next slide is essentially the performance difference of these two burners. So here I'm contrasting the step or two-zone burner, where we have this preheat zone and this combustion zone, and I'm contrasting this against this graded topology, where we're continuously changing the pore diameter and the porosity throughout the burner. Again, looking back to the stability diagram, plotting the equivalence ratio as function of the mass flow rate. This colored region here is the stable operating point. I'm showing here some measurements in yellow, just to confirm that this simulation result is essentially verified and validated. And for comparison, I'm also looking to a free flame system. Now, this is our prior burner that I showed you experimentally in the experimental results in the first part of this presentation. If you're now looking to this continuously stabilized burner, where we're changing the porosity and the pore diameter throughout the burner, you can see a way that the flame is now not anchored at this interface anymore. It can float freely throughout the burner, and depending on the mass flow rate and the operating conditions, you can achieve different combustion zone. And this makes it rather interesting, since now I have a much broader range where I can operate the porous media burner. This translates to a significantly extended operating regime. Here, computation results show this color-coded region is the stable regime, and you're seeing right away that from a stability range of about 2 kilograms per square meter per second mass flow rate, we can extend this almost by a factor of 3, making this a rather interesting porous media burner design for this application. All right. So here the key message is that we can significantly extend the stability limit for this burner. And at the same time, as I'll show you in a second, we can also reduce the emissions simply by taking advantage of this rather broader operation regime by allowing this flame to stabilize at different locations. And this is essentially here facilitated by this continuously graded burner design. Now, two questions is, the first question is, well, how can we manufacture this burner? The second question is there any way that we can experimentally verify this? And I want to show you this in the next slide, where we're going through this process. Here I'm showing you an illustration of this step profile, which we have seen before. What you could do is you could essentially approximate this continuously graded profile by incremental changes in the porosity, where you're seeing here essentially in our first attempt of mimicking this continuously graded design, where we essentially stacking up pore sizes of different diameter in increments and approximating this by differential changes in the pore diameter. As I said, our ultimate goal is to do this continuously graded design. And we work with different companies to facilitate this first design. And this is essentially just taking existing technology and adapting this to our environment. These are systems from 3 different companies. We work with Ultramed. This is a company here in the US. We work with Lanic to get a similar profile, and Engineer is our another supplier where we were able to stack the different structures. But what you're seeing is, as I said, this is suboptimal. You're seeing some gaps. You're seeing some cracks and fractures here. So this is certainly not necessarily the best design, but it turns out that we are already getting some indication that this concept works. So really consider this as an intermediate step. After I can show you the proof of concept, we want to look to some more advanced designs, right? So the improvements of the step profile, of the continuous profile, this incremental profile over the step profile, illustrated here that yes, indeed, we are seeing improvements in the stability by about 30%. It's not a factor of 2, but it's already noticeable, and we're quite pleased that this initial concept is actually working for this design, right? So then the next question is, can we do better? And the answer is yes. And here we are resorting to 3D printing and additive manufacturing in order to get an optimal design of this porous media system. As many of you know or are very familiar with, 3D printing or additive manufacturing is quite a common technology right now. You certainly encounter this on a daily cycle. The key challenge here is that since we are interested in high temperature materials, and in addition interested in ceramic materials, this is a rather hard proposition to utilize additive manufacturing processes, simply for the reason that manufacturing the ceramic materials is a rather challenging endeavor. What we are resorting to is a so-called lithography-based ceramic manufacturing system. And this works essentially in a slurry setup. I'll show you this in a second. And this is one technology that allows us to print ceramic materials in a 3D fashion. And by using this LCM lithography-based ceramic manufacturing, we have fairly good control over the accuracy of the pore structure in replicating the CAD drawing. And at the same time, we have also good control over the material properties of the ceramic structure. So how does it work? This LCM lithography-based ceramic manufacturing, we're starting in 3 processes. The first step is to generate an STL geometry that essentially represents our ceramic structure. The second process is in so-called production of a green part. As I said, this is the sintering material process. We are putting this in a slurry of the ceramic materials. Then we're using a photopolymerization, which is essentially a light exposure on this layer. This essentially retains an initial structure. And the final part is then facilitated by a sintering process, where we're getting our final process parts that we then eventually will characterize and employ in practical applications. So here, in order to design a ceramic structure, we're relying on a predefined topology. This is referred to as triply periodic minimal surfaces, which is essentially geometric or harmonic structures that become combined in different ways. And we have here the flexibility of changing parameters, most notable the wavelengths, or this pore diameter omega, and also an offset parameter q. Depending on this, we can manufacture different structures. And I just want to show you here one of this design by looking to this diamond structure, where we're getting very homogeneous or regular pore sizes, and we are achieving a stratification in the pore diameter along the axial direction. And this is exactly what we wanted to achieve with this continuously graded porous media structures. So what we're seeing here is we are imposing a linear degradation of this wavelengths parameter and also a linear gradation of this offset parameter q. And with this, we can tune in different parameters under constraints of porosity and pore diameter. This essentially turns out to be an optimization problem that is rather easy to solve computationally. Of course, the pore diameters that we are considering here are fairly small, somewhere between 200 micrometers to a few millimeters. This is still a rather challenging endeavor, simply for the reason that the pore structures or the pore diameters are rather small, and with this, the strut sizes are fairly small. This puts quite a bit of pressure on this. We worked quite extensively here with lithos. These are the 3D printing manufacturer in a rather iterative way to end up with a design. But you can see that many of our structures initially looked as this, where we see complete damage, and through this very close and successful collaboration with licensors, we essentially were able to achieve the desired performance. So in total, we have the manufacturing process. We did the analysis, and I want to show you some of the results where we employed SEM and an X-ray tomography system to look to the pore structure, the material stability during the combustion process. And the first result that I want to show you is an SEM image of this pore structures. You're looking here right inside the structures. The scale is about 500 micrometers, and you're clearly seeing the formation of the pore topology, the layer material here, where we're essentially using this sintering process with this very fine structures. Turns out that the layering thickness on how you're operating this manufacturing process determines the stability, and with this we can also control the thermal properties. And I want to show you some results of this as well. The next step, we operated this burner that you can see here in this setup, in this high temperature environment where we essentially exposed this to a combustion product, and performed in cyclic operating test or durability test. I'm showing here SEM images of the structure pre-testing after 1 hour and eventually after 24 hours. And what we observed is that for this silicon carbide, we didn't see any thermal degradation, which allowed us essentially to convince to demonstrate the viability of this system for this high temperature long-term exposure. Another property that is critical is the thermal conductivity. How fast are we conducting heat through this pore structure? Here we explored the feasibility of using different sinter materials, different pore diameters, which is illustrated by this parameter A and B. Depending on the pore diameter, we can control the conductivity. And the second parameter is the layer thickness. Remember, the first layer thickness that I showed you was somewhere 25 micrometers. This is our sintering layer. By modulating this between 25 micrometers and 50 micrometers, we can get different thermal properties, and this makes this rather interesting. So the summary here is illustrated. In this, we did some conductivity tests, and depending on the material properties, we get a rather wide range of operating conditions in this porous media burner using this additive manufacturing. And with this, we have a very good control over the burner characterization. The faithfulness of the process is illustrated here. What I'm showing you here is a CT reconstruction of the pore sizes, the STL geometry, and the XCT geometry. For the pore diameter, we're doing very reasonable. Black is the post-processed or the manufactured structure. The blue line is the geometry, the initial geometry. We were aiming for an homogeneous porosity. We were not quite able to facilitate this, and the reason for this is that we're generating some or obtaining additional material separation on the strut sizes, which changes the porosity, but the pore diameter is very well captured in this environment. And the last test that I want to show you here before I close is the burner testing. Remember, we set out to demonstrate an extended flammability limit, an extended performance behavior of this additively manufactured porous media burner with tunable structures. And this is here one of the main conclusions from this analysis is that if you're using a step topology, you're getting a rather benign stability limit using this additive manufacturing process. By utilizing this continuously graded system, you're seeing that we can significantly extend the operability to extremely high mass flow rates. We had to cut off at some point simply for the reason that our mass flow controllers were maxed out. But overall, you're seeing that this graded topology in conjunction with additive manufacturing processes allows us to tune the performance and at the same time get an extended operability of the porous media burner. Okay, so with this, let me conclude here. I showed you a process that had the goal of exploring and advancing the utilization of porous media structures for combustion applications. I showed you a theoretical analysis that demonstrates the potential of this technology. We demonstrated the feasibility at high pressure and liquid fuel operation, and then we moved into the design a process of exploring continuously graded porous media burners. I showed you a design process that combines computational optimization using triply periodic structures in conjunction with additive manufacturing processes, so that we can go all the way from the practical realization to the testing. We saw a significant extension of the probability limit, but there are still more work to be done, and this has to do simply with the manufacturing process. And I think right now we are hitting the limits here of the manufacturing process, and I think there's more opportunity to advance this technology. So with this, I'd like to thank you for your attention, and I'd be glad to take any questions. Thank you.
Yeah, thank you for that very interesting talk. Are there any questions from the participants on Zoom? Please just raise your hand and then we can give you the right to speak. And here in the audience, also not. I have one question. By having this heterogeneous porous media inside such a gas turbine, don't you run into issues of having local hotspots which you might not be able to identify within the porous structure?
Yeah, that's a really good question. So what we have not seen is hotspots, but because of the cyclic heating and cooling, we're essentially seeing that we have quite some thermal expansion. But maybe I just go to one picture here to illustrate the idea. The porous media burner is certainly a very homogeneous system, and because of this internal dispersion, we're getting a very homogeneous mixing system. So it kind of prevents the occurrence of hotspots under stable conditions. We haven't encountered this. The key challenge is that because of this very strong temperature gradients, you get quite a bit of thermal expansion, and this is really causing material stresses on this system.
Okay, yeah, thank you for the answer. Yeah, if there are no further questions, then I end this lecture for today. Thank you again for your time and a nice presentation, and yeah.
Thank you for the invitation. I appreciate it. Bye.
Have a nice day. Bye.